In this video, we'll learn about the R and S convention for naming chiral centers. Because enantiomers have otherwise identical structures, we need a naming system in order to differentiate between enantiomers. And the convention that we use is called the Kohn-Ingold-Prelog rules. And in this convention, a chiral center is denoted as either R or S. And this slide will walk you through how to determine the R or S designation. And as we walk through the rules, we'll use lactic acid here to the right as an example. First, we rank the 4 atoms directly bound to the chiral center, and we rank them according to atomic number. So the highest atomic number is the highest priority, is number 1. If we have the same atom directly bound to the chiral center, then we move the next atom over and compare those until we encounter a difference. Doubly bound atoms count twice, or as 2 singly bound atoms. In this example, the OH group is the highest priority because oxygen has a higher atomic number than carbon or hydrogen. The hydrogen is the lowest priority. And then we have 2 groups that both have a carbon directly bound to the chiral center. So to rank those 2 groups, we need to move to the next position over. So we compare the hydrogen to the oxygen. The oxygen is the higher atomic number than hydrogen. So the CO2H group, the acid, has a higher priority than the methyl group. Then we orient the molecule so that the lowest priority group is facing away from us. If you have a hydrogen on your chiral center, this will always be the hydrogen atom. And when you reorient your molecule in this way, you can think of it like a Newman projection looking down that carbon-hydrogen bond. Finally, when your molecule is in this orientation with the lowest priority group in the back, you draw an arrow from your highest priority group to your second highest to your third. The directionality of that arrow tells you if your chiral center is R or S. If the arrow is going in the clockwise direction, it's R. If the arrow is going in the counterclockwise direction, it's S. And there are numerous mnemonics to help you remember R and S, but the one that has always stuck best for me is to simply think of a steering wheel. When you turn a steering wheel in the clockwise direction, your car turns to the right. So clockwise is R. The trickiest part of determining the R and S configuration is often reorienting the molecule in the right way. So we'll look at that in a little more detail here. For me, it's easiest if I position the structure so that the lowest ranking group is pointing straight up. Here that will be the black group. Then I just imagine flipping the molecule so that I'm looking down the carbon-hydrogen or carbon-black group bond. When I do that, that puts the white group to your left and the red and blue groups to the right, with the red group toward the top and the blue group toward the bottom. If you don't have a model kit in front of you right now, I'd encourage you to get it and build a basic chiral carbon so that you can practice reorienting the structure with the lowest priority group pointing back. Okay. Now we'll draw it here. So again, with the low priority group pointing up, I imagine flipping the molecule so that I'm looking down the carbon-hydrogen or carbon-black atom bond. When I do that, that puts the white group on my left and the red and blue on my right, with the red group toward the top and the blue group toward the bottom. Okay, and I can determine R or S from here, but the convention is to have one group pointing straight down and the other 2 up to the right and to the left. So I'll just clean up my drawing a little bit to match that convention. Okay, let's try one now. Go ahead and determine the numbering priority for the following molecule, then reorient it and assign it as an R or S enantiomer. To determine the priority ranking of the 4 groups bound to the chiral carbon, I need to look at the atoms directly bound to that carbon. The hydrogen will be the lowest priority, and the sulfur will be the highest priority. The other 2 groups are bound directly through a carbon, so I move one position over and compare the hydrogen to the oxygen. Oxygen's a higher priority, so the acid is ranked as second, and the methyl group is ranked as third. Now to orient the molecule, I imagine myself looking down that carbon-hydrogen bond. If you need to build the model or if you need to redraw it so that the hydrogen is pointing up, then please do. When I look down the carbon-hydrogen bonds, I see the sulfur on my left, the methyl on my right, and the acid group pointing straight down. I add in the priorities and then draw an arrow from 1 to 2 to 3. We'll end this video sequence answering the question we posed at the beginning to draw the structure of S2-pentanol. This question is asking us to go the other way, from a name with a stereochemical designation to a structure. Here we should start by drawing 2-pentanol. Remember that pentanol is a 5-carbon chain with an alcohol, and the position of that alcohol is indicated by the number 2. Now I need to draw in the S configuration, and S will be the counterclockwise orientation of the 4 groups. So I'll rank the groups, and then I see that as drawn, if I just put the hydrogen back, the groups are in the wrong order. So instead I can redraw it, starting with the chiral carbon, placing the lowest priority group back, and the highest priority group forward. Then I can take the second and third priority groups and place them so that the second priority is to the left and the third priority is to the right. This will give me the S configuration. The other way I can draw the S when I realize that my groups are in the wrong order is to put the OH group backward instead of forward and keep the methyl and propyl groups where they are. And if that's hard to see on a 2D surface, build the model and convince yourself that these two drawings are depicting the same structure. They're both S2-pentanol.